So this is my section 5.2 practice problem video for question 107. As per usual, I'm going to start by going over the general concepts of section 5.2 that are takeaways, like the main general concepts that should be kind of remembered and are the biggest components of this subsection. Starting at the beginning, we just start talking about infinite series, like pretty much what they are, like how they come in like what forms. And while we're defining an infinite series, as it goes towards infinity, like say the summation starts at 0 and it goes towards infinity, instead of infinity, for us to test the convergence of this, we can set that infinity to k, and then we can set the entire equation sk equals to the summation of n starting at n equals whatever 2k, and then we can use whatever series it is, like a sub n, whatever it is. And this is how we actually calculate like the partial series, which is pretty much the biggest component of section 5.2. And using that sk equation that I just said, we can also find the convergence of the series. And well, if the series partial sum diverges, then we can also find that it's a divergence of a series. Moving forward, we just kind of move into like what partial sums are, like how they are evaluated, what a harmonic series is, because like a harmonic series is like unique, like we actually talked about it personally. It diverges, but it diverges very slowly, even though we believe that it would converge. And one of the examples is 1 over n, like you would believe that it converges, but it does not. Yeah, so that's pretty much what a harmonic series is. It just diverges very, very slowly, and the sum of those partial sums prove that it is diverging very slowly. The next thing we have is, I guess, like the properties of what a convergent series is in this context. So there are like algebraic properties as well. Like you can take two continuous series, like say we have a sub n and b sub n as two functions over like a summation. The properties are like, if you add a sub n plus b sub n, the summation of both of those added together converges, and it's called the sum rule because you can just add those two summation of the functions together. And same thing with the difference rule, like if it's a summation of n starting at n0 going to infinity, and then you're trying to do the sequence of an minus the sequence of bn, and it converges, then you can find that convergence, like convergent number, like whatever the convergent limit, I guess, is by doing the summation of a sub n minus the summation of b sub n, and the last rule is the constant rule. Like if it's a summation of c, which is the constant, times a sub n, and it converges, then we can take the c outside of the summation actually, so it would be c times the summation of n to infinity of a sub n. So that pretty much is like the algebraic properties of like convergent series. Like if you have like two functions within one summation, then you can use what I just said, the algebraic properties, to find like the convergent limit of it. And then the next big thing is like how to write like geometric series. The general form is a summation of a times r to the power of n minus 1 as it progresses through this summation. And the reason we write it in that form is because what we're ultimately trying to do is get back to that original SK equation that I told you in the beginning of this, and that will help us determine if we have a divergent or convergent series as well. So pretty much how that works is the SK equation I'm talking about is the partial sums equation. And what that pretty much means is when we use the partial sums equation to evaluate a series, and we start adding up the partial sums, we can see whether it diverges, like if the infinite series diverges by we can see if the infinite series diverges by pretty much plugging it into by I guess plugging it into like, sorry, I'm butchering that. What I am trying to say actually is okay, what I'm trying to say is infinite series, a geometric series in the basic form that I mentioned, the summation of a times r to the power of n minus 1, n being the number term it is. If the r value, like the base of the exponent, if the absolute value of that is less than 1, then it converges, and if it is greater than 1, then it diverges. But another condition though is the absolute value of r has to be less than 1, and the summation of that ar to the n minus 1, like of the actual sequence, it has to equal a over 1 minus r. It has to be in that form for it to check out. So that way at least you can know that like if r is less than 1, when you write it as a over 1 minus r, like it can't be equal to 1. Like it has to be less than 1, or else the denominator would be 0, and you can't have 0 as a denominator. So I guess moving forward, I am sure the last thing that I did want to cover is what a telescoping series was. That's pretty much just when you're computing the partial sums, some of the terms cancel out as you go through that summation. So like if you have like an equation where it's like the first term, like it's written out where it's the first term minus, or the second term minus the first term is how you find the second term. When you go to the third term, it would be the third term minus the second term. So the second terms would cancel out, and all you would have is just the first term and the third term. So like if you keep going that way, it would eventually just be the first term minus the last term. So, or minus the last term plus 1. And that is the same as pretty much saying S sub k equals A sub 1 minus B sub k plus 1. So in that equation, k is pretty much like the numbered term in the sequence, like the first term or the fifth term or whatever, and you can find the kth partial sum by doing b sub 1 minus b sub k plus 1. Yeah. And that also is what a telescoping series is, and we can tell if it converges or diverges if we pretty much use those partial sums to find like that final equation that we can just plug our value into to determine its convergency. And I'm going to start the question now. I'm already 10 minutes in, so hopefully I can get through this not too bad. But I've actually chosen question 107 for section 5.2, and that says express the following series as a telescoping sum and evaluate its nth partial sum. So the first thing I'm going to do is write that down, and the equation is the summation as n goes from 2 to infinity, ln of 1 plus 1 over n in close parentheses all over ln of n times ln of n plus 1. Okay. And what I'm going to do first is I'm actually going to rewrite the numerator so I can just have one term inside of the ln instead of 1 plus 1 over n. So I'm going to do this equals ln of n plus 1 over n. Yeah. All over ln of n times ln of n plus 1. And that equals we can actually do ln of n plus 1 minus ln of n on top all over ln of n times ln of n plus 1. And all I did there was I just broke up that numerator. We went from the numerator being ln 1 plus 1 over n to ln n plus 1 over n, which is just rewritten as just one function within that ln. And then the reason we can break it up is ln of n plus 1 minus ln of n does equal ln of n plus 1 over n. And the reason we're breaking this up is because the ln of n plus 1 exists in both the numerator and the denominator, and that way we can try to at least cancel it out. So what we're going to do next is I'm just going to show you right here. That's where I am right now. And I'm going to try to keep simplifying that down until we get to like some sort of partial sum that we can start working with. So I'm going to try to simplify this ln of n plus 1 out. So Okay, so what we can do is, since it's negative, so since it's ln n plus 1 minus ln over n, and there's also an ln over n at the bottom, we can do 1 over ln of n minus 1 over ln of n plus 1. Yeah, yeah. Yes, so the final one I got is 1 over ln of n minus 1 over ln of n plus 1, and that's just after I simplified it, and that would also make it easier for when we go in and start plugging in values to try to evaluate this. And the first thing we're going to do is start with the first value, which is s at 2. So what we can do is at s at 2, this equals 1 over ln of 2 minus 1 over the ln of 3. And then we can, I guess, keep going to try to find, like, move towards infinity to try to find where it starts canceling out and what we can get as like a more contained general form of this series. And so I'm gonna keep going. I'm gonna say S3 equals 1 ln of 2 minus 1 over ln of 2 minus 1 over ln of 3 plus ln of 1 over ln of 3 minus 1 over ln of 4. Yeah, so as we can see here, there's a negative 1 over ln of 3 and a plus 1 over ln of 3. So those cancel out, and for S3, we're just left with 1 over ln of 2 minus 1 over ln of 4. So we can kind of start seeing here that I believe the numerator is going to have a somewhat an even factor to kind of like build this up. So I'm going to try SF4 here. It's just 1 over ln of 2 minus 1 over ln of 3 plus 1 over ln of 3 minus 1 over ln of 4 plus 1 over ln of 4 minus 1 over ln of 5 . Yeah, so what's happening here, cancel out the 3's, cancel out the 4's, and we're left with S4 equals 1 over ln of 2 minus 1 over ln of 5. So actually, it's not going to be like an even term. I don't know why I said that. Sorry about that. We are trying to find that S of k equation, the general form of this. So as you can see, it's going to be S sub k is always going to be 1 over the ln of 2 minus 1 over the ln of k plus 1. Yeah, so this is the partial sum that we finally come to. this is the partial sum we finally come to, which is pretty much just, we got that by pretty much just evaluating up until s at 4, the sequence at its fourth component, and then figuring out that no matter what it is, like whatever the number is, like third, fourth, or fifth component, it'll always be 1 over ln of 2 minus 1 over ln of k plus 1. So from here, we can pretty much say that this entire function s of k like its partial sum expansion, like its nth partial sum, will always be less than 1. It'll always be less than 1, and because of that, the series does converge as, yeah, so the series converges because, as you remember, like again, we're trying to get it into that equation, like that equation that I will show you right now. And if we can show that the value, like if we can show that the partial sum like value, like at whatever term it is, approaches either 1, like if it is less than 1, then it will always converge, but if it is equal to 1 or greater than 1, it will always diverge. So since no matter what value you plug into s of k, it'll always be less than 1, the series does converge. And this is my final work for this. And yeah, thank you. I believe that is it for section 5.2.